Good evening, students.
Good evening, sir.
Yeah, so we'll start the class in less than 5 minutes. I want you all to go through the concepts that we have discussed till now. So I'm just giving you 2 minutes time. Go through the concepts and then we'll get started. Yes, students. Is there any doubt from the previous topics that we have discussed? Is there any concept that is not clear from previous class discussion? So everything is clear then? No doubts. Okay then, we'll go to the next part of the chapter. It will be maximum done in 20 minutes because it's full of theory. Okay. Topic that we are going to discuss is called as atmospheric refraction. So please write down the heading as atmospheric refraction in your textbook. Okay. See, generally, have you ever observed this kind of a thing? You might have observed the apparent random wavering or flickering of objects seen through a turbulent stream of hot air. Just a minute. See, have you ever seen this kind of a thing, guys? When you go on a road, like if you look at the road, right, it will appear as if there is water. But when you go close, you will see that there is no water or something like that. Have you ever observed like this?
Yes, sir.
Yes, sir.
Yes. So this kind of a phenomenon is called as mirage actually. And this happens because of a principle called as total internal reflection. Okay. So let me explain what that concept is actually. Okay. So generally, or else if you see, try to look at the objects. I'm not sure if you guys have observed this. I don't get images of it. So if you're suppose standing here and let's say there is hot air moving like this, you try to look at the objects on the other side. It will appear as if the object on the other side will be flickering or wavering. Right. So that is what happens. So you will. So there are two types of positions. So the object on the other side has a true position associated with it. So what do you mean by true position? So true position means if I take some reference, okay. So for a person sitting on this side, let's say the person sitting at the origin, they'll be able to see the object at a particular coordinate. Okay. But when you look at this, will this point be stable or will it be moving? So there will be a kind of wavering or a flickering effect that will take place. Okay. So when you see through, that's the point given there. You might have observed the apparent random wavering or flickering of objects when you see through a turbulent stream of hot air rising above a fire or a radiator. Okay. So what do you mean by turbulent stream? Turbulent means something which is not moving in a steady manner. Okay, the smoke itself will move like this. It will not move in a steady manner, right? So when you look at the object on the other side through these many layers, what will happen is the shift of the object's position will take place. Okay, and that position is called as the apparent position. I hope I'm clear, right? So why is this happening? The air just above the fire becomes hotter than the air further up. So if this is the fire, okay, there is different layer of air. There are different layers of air. I hope you guys are able to understand, right? So 1, 2, 3, like if I take these layers, now you guys logically tell me if I take this as fire, guys, which layer will be hotter? So will it be layer 1, 2, 3? Which layer is going to be hotter?
So layer 1.
Layer
First
1.
layer.
Reason? Obviously. Reason? Because it is the one which is closer to the fire, right? So have you ever heard this, that gases expand on heating? Right? So you have a layer of air, right? That air will expand on heating. So when I say expand on heating, its volume will increase. Am I right, guys? Are you guys able to understand the logic? So layer 1 will occupy more volume than layer 2. Accepted? So volume of layer 1 is greater than the volume of layer 2. Now, what will happen to the density? So what is density, guys? Density is mass by volume. So density and volume are inversely proportional to each other. When volume 1 is greater than volume 2, can I say density 1 is less than density 2? Guys, are you able to understand what I'm trying to say? Does it make sense? See, if you understand, let me know yes. If you don't understand, ask, I'll tell. Am I clear? Okay. So the hotter air is lighter, that is less dense than the cooler air above it, and has a refractive index slightly less than that of the cooler air. So what will happen is the layer above the fire will be less dense compared to the layer above it, and there will be a difference in the refractive index. Since there is a difference in the physical conditions of the refracting medium, that is air, so the refractive index of the medium itself is not stationary. Then what will happen is The apparent position of the object as seen through the hot air fluctuates. So this wavering is thus an effect of something called as atmospheric refraction, because this is happening in the atmosphere that we are seeing. Atmospheric refraction, that is refraction of light by the Earth's atmosphere on a small scale in local environment. Okay. So due to this, what are all the phenomena that you are able to observe? The twinkling of stars is a similar phenomenon on a much larger scale. So we will try to understand why stars twinkle. Okay, now we'll discuss about twinkling of stars. So if this is the star, right? So from the star, what is going to happen? The light rays will start traveling through the atmosphere, right? So when the light, had this atmosphere not been there, what would have happened? The light would have traveled through the vacuum in a straight line path. But due to the atmosphere, what is going to happen is there will be a refractive index decrease taking place. Sorry, there will be an increase in the refractive index taking place as you move from the star towards you. When that is happening, the ray will start bending due to the atmospheric refraction. That is the concept. See. So the twinkling of stars is due to the phenomenon of atmospheric refraction of starlight. So starlight on entering the Earth's atmosphere undergoes refraction continuously before it reaches the Earth. Okay. So this atmospheric refraction is taking place in such a medium of gradually changing refractive index. Okay, let me give you another example for this. If suppose there is a transparent glass of water like this, and you drop a stone, okay? You drop a small stone into it, then what will happen to the stone? Due to the density difference, the stone will be found at which position? Can you answer that? Where will the stone be found, guys? Hmm? Yes, I'm asking you only. Where will the stone be found? Okay, I'll better read it out. You mark it in your notes. Okay. So, since the atmosphere bends starlight towards the normal, the apparent shift of the star is slightly different from that of its actual position. Okay. As a result of it, the star will appear at a slightly higher position than its actual position when viewed near the horizon. Further, this apparent position of the star is not stationary but keeps on changing slightly, since the physical conditions of the Earth's atmosphere are not stationary, as was the case in the previous paragraph. Okay. Since the stars are very distant, they approximate point-sized sources of the light. As the path of rays of light coming from the star goes on varying slightly, the apparent position of the star fluctuates and the amount of starlight entering the eye flickers. The star sometimes appears brighter, and at the other time it will appear fainter, which is called as the twinkling effect. And this is happening only due to the principle of atmospheric refraction. Okay, you can make a note. It'll be like this only. I told you on previous class itself, if there is going to be no response, I'm not going to teach. Okay. The next question that you'll get in your exam is, why don't the planets twinkle. Okay. The reason is very simple. The planets are much closer to the Earth and thus seen as extended sources. If you consider the planet as a collection of large number of point-sized sources of light, the total variation in the amount of light entering our eye from all the individual point-sized sources will average out to 0. Therefore, they will nullify the twinkling effect. Okay, there is a reason that they will ask you, you mark it. Okay.
Okay, sir.
Sir, can you explain why don't the planets twinkle?
Why are you guys not responding when I'm asking something? I asked you guys 5 times about what will happen to the stone. What is your problem on opening your mouth and speak? Whether it is right or wrong, have I ever scolded or said anything, criticized anything like that? I'm trying to have a discussion, right? You guys don't ask, then what do I do? There is nothing to teach actually in this. It's a self-study chapter, full of theory. Listen. So, did you understand why star? At least answer now, okay? Did you understand why stars twinkle?
Yes, sir.
Yes, sir.
Yes, you guys understood that, right? If I have to explain it, see what will happen is I'll show you certain diagrams. If I take different layers, guys, if I say this is oil medium, okay, and if I say this is water, you know that oil will float on top of water. We know this fact. Why is it happening? Because oil is less dense and this is more dense. So when light is hitting the surface, what will happen? When light is hitting the surface, if this is I, and if I take this to be air medium, then the refractive index of air is greater than is less than the refractive index of oil. Correct? So what will happen to the light? The light will start bending towards or away from the normal. When light is traveling from denser to rarer to denser medium, what will happen? Rarer to denser, what will happen to the light? Will it bend towards the normal or away from the normal?
Sir, away from
So
you.
towards the normal.
It will bend towards normal. It will bend towards the normal. Okay. Then again, if you draw a normal, refractive index of oil is less than refractive index of water. For example, let's assume it to be like this. Now what will happen? Again, it is traveling from rarer to denser. So it will bend more towards the normal. Are you guys able to understand? So
Yes,
if
sir.
an object is here actually, if you see from here, then where will you be able to see the actual object? You will not be. So if you backtrace it, you will feel as if the object is here. So this is called as the true position and this is called as the apparent position. So this is the same example with respect to atmosphere also. If you observe in the downward direction, the refractive index is increasing. Okay. Now try to connect all the dots and understand what is happening here. Okay, now let's understand point by point. So the twinkling of star is due to the atmospheric refraction of starlight. So this is the object. When the starlight is entering the Earth's atmosphere, it undergoes refraction continuously, like how oil, water, different kinds of layers are there. Each layer of the atmosphere itself, see, each layer of atmosphere is not made of oil, water, or something like that. It is because of the difference in temperature or whatever it is, there is an atmospheric refraction that is going to take place continuously before it reaches the Earth. So the atmospheric refraction occurs in a medium of gradually changing refractive index. This is accepted. So how is the refractive index changing? Is it increasing as you move down or is it decreasing? This might be a question. So refractive index is increasing. So as it is increasing, the atmosphere bends the starlight towards the normal. Now you are able to understand why it is bending towards the normal. It is because of the same example that I gave you. It bends towards the normal, as a result of which the apparent position of the star is slightly different from its actual position. Like how I showed you here. So what will happen is the actual position is here, but for the person who is seeing from the other side of the water will feel as if the object is slightly lifted above. Okay. Are you guys able to understand?
Yes,
So
sir.
when viewed near
Yes,
the
sir.
horizon, further, this apparent position of the star is also not stationary. You can ask me a question, sir, is this position going to be stationary? No. Why? That position is not stationary because the physical conditions keep on changing with respect to time, but keeps on changing slightly since the physical conditions of the Earth's atmosphere are not stationary, as was the case in the previous paragraph. So in the previous section, what did we see? This effect itself is happening because the atmosphere, the physical conditions of the atmosphere is not stable. Since that is continuously changing with respect to time, the apparent position of the star will also keep changing with respect to time. Right? But one thing is, since the stars are very distant, they are very far from us, they are approximated to point-sized sources of light. That is why you will see like a point source because of the distance. As the path rays of light coming from the star goes on varying slightly, as the path of rays coming from the light, as the path of rays of light coming from the star goes on varying slightly, the apparent position of the star fluctuates and the amount of starlight entering the eye keeps flickering. Are you able to understand? So it will appear, it is due to this atmospheric, so the star is actually at that position only. But due to the atmospheric refraction, we will feel as if the star is moving from one position to another. Okay. The apparent position of the star fluctuates and the amount of starlight entering the eye also keeps flickering. Then what will happen is, due to this kind of a phenomenon, sometimes you can see that it is brighter and sometimes it will appear fainter, means it is less intense. That is the reason why the twinkling effect is actually taking place. It is stable only, but we feel as if it is twinkling. Okay, it is actually an effect. Okay, now with this phenomenon, if you ask a question like, why don't planets twinkle? The answer is, the planets are much closer to the Earth. Unlike stars, the planets are much closer to the Earth and they are seen as extended sources. What do you mean by extended sources? See, their source means, you know, right? That is a source of light. So source means something which is under study for us. Okay. If you look at the star is appearing like a point-sized object, but the planet will be seen like an extended object. Okay, this is the meaning of extended source. Extended source means finite sourced object. Now, if you consider this planet as a collection of small, so on this planet, what you can say is there are multiple small objects connected together is what is making this planet. Guys, you're able to understand? If we consider a planet as a collection of large number of point-sized sources of light, the total variation in the amount of light entering our eye from all the individual point-sized means from this individual source, there will be a light entering our eye. From this individual source, there will be light entering our eye. So when all these lights are entering, what will happen is the average value of all these effects will be in such a way that they will get cancelled out. Means one might be flickering, one might be fainter. So if you see a flickering and a fainting object at the same time, what will happen? You will feel as if nothing is happening. Like if I say, I can give you a mathematically. If I call flickering as positive, brighter as positive, the dull one as negative, then the positive and the negative effect put together will give you a nullified effect. You're able to understand? So that is what they're saying. The total variation in the amount of light entering our eye from all the individual point-sized sources will average out to zero, thereby nullifying the twinkling effect. That is the reason why planets do not twinkle. One of the reasons is they are closer to the Earth. Since they are close to the Earth, they are treated as extended objects, which are nothing but collection of many point-sized objects, and the twinkling effect due to individual point-sized objects is nullified. Am I clear? Does it make sense?
Yes, sir.
Yes,
Right.
sir.
So this
So
is the
your
reason.
extended sources mean like it is large.
Extended means it is large.
Okay, sir.
Okay, see, I'll give you an example. See, suppose you have a pen in your hand, right? You look at the pen in your hand. Let's say the tip of the pen is in the upward direction. You're keeping it like this. Okay. So when you're looking at the pen from where you are sitting, is it appearing like a finite sized object or a point sized object? You can just guess. So you have a pen in your hand, the one with which you are writing. You just keep the pen in such a way that the nib is pointing upwards and you're looking at it. Are you able to see it comfortably? Are you able to see the bottom and the top of the pen comfortably?
Yes, sir.
Yes, sir.
Right? And the pen has a finite size associated with it. Right? The pen has a finite size. Suppose, let's say you're standing in a ground, okay, and you're keeping the same pen, and there is another friend of yours who's very, very far. Okay. If you ask your friend to look at the pen, will your friend look at the pen as a finite sized object or a point sized object?
Point size.
It will
Point
become point.
sized.
The same thing is happening with stars and planets. Okay, it is like we are close to this pen, that is a planet, and stars are very, very much far from us. So since you are close to it, you are able to see it as an extended object. Whereas for the person who is very far, though it is finite sized object, it is appearing like a point sized object. That is why we call it as an effect. You're able to understand?
Yes, sir.
So extended means that is the meaning. It is of some finite size. That is the meaning of extended. Okay. The next application is advanced sunrise and delayed sunset. So the sun is visible to us about 2 minutes before the actual sunrise and about 2 minutes after the actual sunset because of this principle, atmospheric refraction. So what do we mean by that? By actual sunrise, we mean the actual crossing of the horizon by the sun. Okay, so what is horizon? It is a layer which separates the Earth's surface and the atmosphere. Okay, horizon is a layer which separates the Earth's surface and the atmosphere. So what will happen is, because of this atmospheric refraction, by actual sunrise, we mean the actual crossing of the horizon by sun. So in figure 1.10, we can see that the actual and the apparent positions of the sun with respect to the horizon. Okay, so you're the observer standing here on the surface of the Earth. When you look at the sun near the horizon, okay, this line, when you look at the sun near the horizon, this is the layer I'm trying to talk about. Okay, this layer is called as horizon. So sun is here, the light is coming in this way. So what will happen as the light is traveling through the atmosphere, it undergoes atmospheric refraction. Let me take another. It undergoes atmospheric refraction and it enters your eye. But what will happen is it will appear as if it is here. So this is also an effect only. This is actually not happening, but we feel as if this is happening because of the atmospheric refraction. Okay. So what are the two effects that you can observe due to the atmospheric refraction rays? One is sprinkling of stars and the second is advanced sunrise and delayed sunset. Okay. And the last phenomenon that you can see is scattering of light. So what do you mean by scattering of light? So name is suggesting, no? What do you mean by scattering of light? See, what do you mean by scattering? Okay, forget about light. What do you mean by scattering?
Spreading.
Yes. So it is something like spread, or it is like a disturbed structure. See, for example, I give you 5 balls in your hand. Okay. And if you keep those 5 balls on a table in an organized way, you can say you have arranged them. But what will happen as soon as you drop all the 5 balls together on the floor? Will they go and stick to the floor, or what is the effect you'll observe? You will observe that each ball will start traveling in some random direction. Right? Let's say you're taking all those 5 balls with 2 hands and you drop them on the floor. What will happen? After collision with the floor, you can observe that the balls are scattered. Right? So the same kind of a phenomenon is exhibited by light also. Okay. The interplay of light with objects around us gives rise to several spectacular phenomena in nature. Phenomena is a plural of phenomenon, means there are several things that we are able to see in the surface because of the different properties exhibited by light. Okay. So one of them is the blue color of the sky, the color water of deep sea, the reddening of sun at sunrise and sunset are some of the wonderful phenomena which we are familiar with. Okay. So in the previous classes, you would have learned about the scattering of light by colloidal particles. Have you learned this in chemistry?
Yes, sir.
Call it as Tyndall effect. Right?
Yes, sir.
So the
Yes,
path
sir.
of beam traveling through a true solution is not visible. However, its path becomes visible through a colloidal solution where the size of the particle is relatively large. Okay. So I cannot go deep into this concept. There is something called as, you can just know the name, okay? Don't get confused with it. There is something called as Rayleigh is the name of a scientist. Scattering of light. Okay. So he is the one who explained about what happens when the light collides with small particles whose size is comparable to the wavelength of light. Okay, so I told you, right, I can't go deeper because I told you what is light. Light is an electromagnetic wave. I'll stop with that because if I go into the concept of wavelength and everything, you will get confused. Okay, so have this point in your mind: when light is going and hitting a particle whose size, if the size of the particle is comparable to the wavelength of light that is hitting the particle, then what will happen is the light will start getting scattered. Okay, due to the scattering of light, we are able to observe certain natural phenomena in our atmosphere. Okay, so the first effect that we are going to discuss is Tyndall effect, and the second is why is the color of the sky blue, and the third is why is the color of sunrise and sunset red. Okay.
Sir, could you repeat scattering of light once more, sir? I had some connectivity issues, sir.
Which one? Scattering of light.
Yes, sir.
Okay. Scattering of light, what I'm trying to say is, see, if I have to give you an example, something like this. See, let's say there is a wall. Okay. If you throw a ball against the wall, what will happen? The ball will go and hit the wall. And after collision, what will happen to it? It will rebound. It will bounce back, maybe along the same path. Okay, depending on with what speed you're throwing. If suppose instead of throwing it like this, if I throw it like this, what do you think will happen? Will it come back in the same path?
No, sir.
It will start traveling in some random path, right? It might have, see something, I drew a random diagram where this kind of a phenomenon can be observed. Okay. So here if you observe, why is the ball's direction changing? So what is the phenomena which is trying to change the direction of the ball? It is collision. I hope you guys understand what is the meaning of collision. For example, you play cricket. When the ball comes and hits the cricket bat, we call it as collision. Right? The ball will come in one direction. When the batsman hits it, it goes in another direction. Right? He changes the direction of it. Right? I hope you guys are able to visualize that. In a similar way, imagine ball as light and the bat as some small particle. When light comes and hits that small particle, what will happen is, due to the process of collision, and depending on at which point it is getting collided, that is on a microscopic level, depending on at which point the light is getting collided, the direction of the light will start changing. Right? So the light was actually traveling in this part. Let's say you have a screen here. Let's say you have a screen here. If the light is coming and falling on the screen continuously, what you did is you try to bring in some small particle here, due to which you are able to observe that the light is falling here. So what has happened actually? What did you do? You actually changed the path, that is the direction of the light in which it was supposed to travel. This kind of a phenomenon, if you're able to observe, this is what is called as scattering of light. Clear?
Yes, sir.
Yes. So some of the naturally occurring phenomena that you're going to see is Tyndall effect. Then why is the color of the sky blue and the color of sun at sunrise and sunset? Okay. So generally, if you look at the Earth's atmosphere is a heterogeneous mixture of minute particles. So what do you mean by heterogeneous? It's a combination of many different particles. Homogeneous means same nature. Heterogeneous means different nature. So Earth's atmosphere is a heterogeneous mixture of minute particles. So these particles include smoke, tiny water droplets, suspended particles of dust, and molecules of air. So when a beam of light, like how I told you, this is one of the rays I considered. What do you mean by beam? Set of parallel rays. When a beam of light strikes such fine particles, the path of the beam becomes visible. Okay. So as a result of which, what will happen is the light reaches us after being reflected diffusely by these particles. Okay. Are you guys able to understand till this point? Is it clear? Right. So you'll be able to answer if any of the points is asked on this. Right. So the phenomenon of scattering of light by the colloidal particles gives rise to the Tyndall effect, which you have already studied in class 9. So this phenomenon is seen when a fine beam of sunlight enters a smoke-filled room through a small hole. Okay. Let's say there is a room which is filled with smoke, and the light is entering through a small hole into this smoke-filled room. You will be able to observe this kind of a phenomenon. As a result of which, what will happen is you will actually be able to see those particles. Okay. So due to this kind of a phenomenon, due to the scattering of light, the particles become visible. Okay. Are you guys able to understand? So this is what is called as Tyndall effect, guys. Okay. So here the important point that I would like to mention is the color of the scattered light depends on the size of the scattering particles. You guys remember I told you, when light rays are falling on objects, if the object size is comparable to the wavelength of light, you know this fact, right? That each light is going to have different wavelengths. You guys know the fact, right? It is because of this effect only what is happening. You're able to observe the spectrum in prism, where violet light is bending the most and red light is bending the least. Right? So when light rays are hitting the particles whose size is comparable to the wavelength, then you will be able to see different kinds of colors, depending on what is the size of the particle the light is encountering with. Okay. So the color of the scattered light depends on the size of the scattering particles. Very fine particles scatter mainly blue light, while particles of larger size scatter light of longer wavelengths. Okay. So if the size of the scattering particles is large enough, then the scattered light may even appear white. This is what is going to happen. Okay, I will show you what exactly it is. So violet light is going to have a wavelength of 400 nanometer and red light is going to have a wavelength of 700 nanometer. Okay, so these are the actual values. So which light? So now see, which light is having the lower wavelength? Guys, which light has the lower wavelength? It is the violet, right? That is what they mentioned here. See, very fine particles, means small size particles scatter mainly the blue light, while particles of larger size scatter light of longer wavelengths. Okay. So if the size of the scattered particle is large enough, means if it is more than the size comparable to the wavelength of light, then what will happen is, then the scattered light may even appear white. Okay. So this is all about the Tyndall effect. Okay. Next. The next point is, why is the color of the clear sky blue? Why is it you're actually seeing it in blue color? It is also because of the scattering of light only. So wherever you see scattering of light, what are the two important things to be remembered in your mind first? One is size of the particle, and the second is wavelength of light which is falling on it. Okay. So let's see what is the reason for it. The molecules of air and other fine particles in the atmosphere have size smaller than the wavelength of the visible light. Okay. So if you look at the molecules of air and other fine particles in the atmosphere, they have size smaller than the wavelength of visible light. These are more effective in scattering light of shorter wavelength. That's what the previous point told us. Right? The size is proportional to the wavelength of light, then they will be able to scatter more. Right? So these are more effective in scattering lights of shorter wavelengths at the blue end than the longer wavelengths which are at the red end. I told you, right? Violet light has 400 nanometer and red light has 700 nanometer. It is because of the small sized particles that are present in the atmosphere, they are able to scatter smaller, they're able to scatter light with smaller wavelength. Okay. So the red light has a wavelength about 1.8 times greater than the blue light. Observe. Here blue means they are referring it to violet only. Okay. Thus, when sunlight passes through the atmosphere, the fine particles in the air scatter the blue color, which is the shortest wavelength actually. Okay. More strongly than red. So it is that scattered blue light because of those small size particles that enters our eyes, due to which we are able to see that the sky to be in the blue color. Guys, are you able to understand? So what is happening? You have molecules of air and other fine particles, due to which smaller wavelengths get scattered, and in that smaller wavelengths, the blue gets scattered the most, and that is the reason why the sky appears to be blue in color. Now the next question is, what if Earth had no atmosphere at all? If there was no atmosphere, then there is no concept of scattering at all. Then what would have happened is the whole sky would have appeared or looked dark. Okay, and that is the reason why the sky appears dark to passengers flying at very high altitudes, as scattering of light is not prominent at such heights. Okay. So one of the real-time applications that they use is, we might have observed that danger signal lights are red in color. You can take the traffic signal also as a reference. Right? Red is more important because people have to stop. Right? So if suppose there is a foggy day or something, or smoke is present in the atmosphere, the red will be able to travel. Okay. So the red will be able to travel a certain distance. That is the reason why they use red color. It is because of the wavelength of the color only. So read this point. So you might have observed that danger signal lights are red in color. You know why? Because the red is least scattered by the fog or smoke. Therefore, it can be seen in the same color at a slightly greater distance also. Why is it not getting scattered? Because its wavelength is more compared to the size of the particles through which it is traveling. Okay.
Yes, sir.
Okay. So this one I will try to show a video. Just a minute. So no, see.
Sunlight is all around us, but we cannot see its rays everywhere. We can see the sun rays clearly when sunlight enters a dusty room. Do you know why this happens in a dusty room? This happens due to the scattering of light.
Guys are able to see due to scattering of light what will happen. Have you ever seen small particles also when you have a dusty room like this?
Yes, sir.
Those particles you're able to see
Yes,
only
sir.
because of this kind of a phenomenon.
By the dust particles present in the dusty room. Small solid particles, here dust particles, suspend in a fluid, here air, are known as colloidal particles. The phenomenon of scattering of light by the colloidal particles is known as the Tyndall effect. The same effect can be observed when sunlight passes through the trees of a dense forest.
So when the same sunlight is passing through trees in a dense forest, you can observe this kind of an effect. This is also called as Tyndall effect.
Here, tiny water droplets in the mist scatter the light. Let us do an activity to observe the Tyndall effect. For this, place a strong source S of white light at the focus of a converging lens L1.
So what do you think will happen, guys? There is a source S and there is a, what kind of lens is used?
Converging lens.
Sorry?
So converging lens.
Yes, converging, right? So what will happen to the light rays? They will come closer, right?
This lens provides a parallel beam of light. Allow the light beam to pass through a transparent glass tank T containing clear water. Next, allow the beam of light to pass through a circular hole C made in a cardboard and obtain a sharp image of the circular hole on a screen MN using a second converging lens L2. As you can see, the path of the beam of light passing through the clear water, that is, true solution, is not visible. Next, dissolve about 2
Okay. So did you understand when you do this activity?
Obtain a
Did you
shot-
guys understand what exactly has happened?
beam to pass
So after the light has passed through the first converging lens, you're able to observe that the light from the source is actually diverged, and due to the converging lens, it becomes a parallel beam of rays. And that parallel beam of rays, when it is passed through a true solution, what has happened? You're not able to see the light passing through that true solution.
through a transparent glass tank T containing clear water. Next, allow the beam of light to pass through a circular hole C made in a cardboard and obtain a sharp image of the circular hole on a screen MN.
So why do we have a screen on the other side? To understand whether light is actually traveling to the other side or not. But if you observe in this activity, you're able to see the light getting collected on the screen, but you're not able to see the light passing through the true solution. So in order to see the light through that solution, what we will do is we'll add some impurities.
Using a second converging lens L2. As you can see, the path of the beam of light passing through the clear water, that is, true solution, is not visible. Next, dissolve about 200 grams of sodium thiosulfate or hypo in clean water in the tank. Add about 1 to 2 milliliters of concentrated sulfuric acid to the water. What do you observe? The path of the light becomes visible through this colloidal solution. In about 2 to 3 minutes, you will find fine microscopic sulfur particles precipitating. As the sulfur particles begin to form, you can observe blue light from the 3 sides of the glass tank. When viewed from the 4th side of the glass tank, facing the circular hole at first, an orange-red color and then a bright
Are you able to understand?
Yes, sir.
crimson red color are observed on the screen. This happens due to the scattering of light by minute colloidal sulfur particles, that is, the Tyndall effect. The Tyndall effect can
So that is the reason why you are able to see the sun as red in color.
also be observed in the atmosphere and can explain some wonderful phenomena of nature, such as the white color of the clouds, the blue color of the sky, and the reddening of the sun at sunrise and sunset. The Earth's atmosphere is a mixture of minute particles. These particles include smoke, tiny water droplets, suspended particles of dust, and air molecules. When sunlight strikes these particles, it gets scattered by the particles, and the scattered light reaches us. The particles scatter a particular color of the scattered light, and the color of the light that gets scattered is the color of the light we see. Let us now understand how it makes the clouds appear white. The clouds consist of large water and ice particles. These large particles scatter all the 7 constituent colors of white light VIBGYOR equally. Thus, the light we see is the combination of all colors, that is, white light. This gives a white appearance to the clouds. Let us now come to the blue color of the sky. The molecules of air and other fine particles in the atmosphere are of very small size. These are more effective in scattering light of shorter wavelengths, that is, blue light. Thus, when sunlight passes through the atmosphere, the fine particles in the air scatter the blue color of shorter wavelengths more strongly than the red color of longer wavelengths. The scattered blue light enters our eyes, due to which we see the sky as blue. Let us now try to understand how
Now, did you guys understand why the sky is appearing as blue?
Yes, sir.
Right.
scattering of light makes the sun appear red at sunrise or sunset. At the time of sunrise or sunset, the sun is near the horizon. The light from the sun near the horizon passes through a large distance in the Earth's atmosphere before reaching our eyes. While traveling through this large distance, the blue light scatters away in all directions before reaching our eyes. Thus, at the time of sunrise or sunset, the light that reaches our eyes is of longer wavelengths, that is, red, and the sun appears reddish. It will be interesting to know that if the Earth had no atmosphere, there would not have been any scattering. Then the sky would have looked dark. Let's recap.
Did you understand, guys? Now what will happen is, so this activity they showed us, right? So in this activity, what are we supposed to do? If you allow a beam of light to pass through the circular hole, now yes, dissolve about 200 grams of sodium thiosulfate in about 2 liters of clean water in the tank and add 1 to 2 ml of concentrated sulfuric acid. Then what did you observe? This side it was red, and you could observe that red light got collected here, correct? The same thing is going to happen to the atmosphere also. So this is the point. Why the sun appear red? It is because light from the sun near the horizon passes through thick layers of air and larger distances in the Earth's atmosphere before reaching our eyes. So during this process, what will happen is, however, light from the sun overhead would travel relatively shorter distance. At noon, the sun appears white as only a little of blue light and white light are scattered near the horizon. Most of the blue light and the shorter wavelengths are scattered away by the particles. Therefore, the light that reaches our eyes is of longer wavelengths. This gives rise to the reddish appearance of the sun. So what will happen is, when the light is traveling for a longer distance, the blue color is already scattered, due to which the longer wavelengths are only able to travel a farther distance. Okay, and the longer wavelength is obviously available for red. So that is the reason why it is appearing red in color for us during the time of sunrise and sunset. Okay, so this is all about scattering of light. So what did we see? We saw atmospheric refraction and its applications. Then we saw scattering of light and its applications. Right. So this is full of theory chapter only, and you guys read it once again and try to answer these questions. That's it. So since you don't have human defects and all other things, we need not worry about it. With this, the term 1 syllabus is over. If there is any other doubt or anything you want me to explain again, you guys reach out to me personally. So depending on the number of requests, I will explain it. If there is anything you want me to explain a different way, I will try to do it. Okay. Any other doubt, guys, from today's class?
No, sir.
Okay. Okay, then we can wind up.
Thank you, sir. Thank you, sir.